All right. Hello, everyone. Welcome back to another video. The problem that we're going to be looking at today is one that I find particularly challenging, so I thought it would be worthwhile to share to all of you. And it deals with topics in asymptotic analysis, which is not something that I had ever seen before. So again, this is definitely something that I would recommend taking a look at because I'm not sure this is covered in every curriculum. It's actually a problem from the January 2013, a notoriously difficult comp exam. And it is question number 1. The question reads as follows. For each real number, x is not equal to 0. It's something to pay attention to. Let theta of x be the unique number such that e to the x minus 1 is equal to x e to the theta x times x. And then we are going to be computing the limit, right, as x approaches 0 of theta x. Now, what we have here, right, is theta x, which is a function of x. It's something in terms of x, right? And we have this equation that I've highlighted in purple that's given by e to the x minus 1 is equal to a bunch of other stuff. This is an implicit equation, right? Because we don't have something that's necessarily in terms of just theta x or just x, right? So we have something that's a little bit more complicated. And when I first saw this, my first instinct was to rewrite this equation to become an explicit equation in terms of theta x. And that is actually absolutely possible. And that will give you theta of x is equal to ln e to the x minus 1 over x, the whole quantity over x. And while this is a legitimate form of the same equation, it's actually going to be very, very difficult to take the limit of this right-hand side right here. It's actually going to be very difficult to compute, and even using L'Hopital's rule is going to provide some complications. So this is actually not the best way to do it. The best way to do this is actually to use the Taylor series expansion, which I will abbreviate here as TSE. And we're specifically going to be looking at the Taylor series expansion for e to the x, because that is one very important key component in this equation. So we actually know, and if you don't have this formula memorized, this is a good one to know, e to the x is going to be equal to 1 plus x squared over 2 plus x cubed over 6. And it keeps on going forever, obviously, right? But because we really only care about the initial terms of the series, especially as x is getting smaller and smaller, what we can do is we can abbreviate that like this, higher order terms. So that is the Taylor series expansion, and we're actually going to substitute that in, right, to our equation, which I will write again. E to the x minus 1 is equal to x times e to the theta x times x. Awesome. So this is our initial equation, and we're actually just going to plug in the Taylor series expansion right on the left-hand side. So that's going to give us this. And because we really only care about the first few terms, actually everything after that x squared over 2, I'm just going to put a dot, dot, dot. We don't really care about that. We get a minus 1, right? And that is going to look like this. So we can do that, right? And then what do you notice? Immediately, we have two things canceling out, right? The minus 1 on this side and the plus 1, those are going to cancel. We can also go ahead and divide both sides by x. So combining both of these steps, right? That's actually going to give us the following. Let me switch colors for a sec. That's going to give us 1 plus 1/2 x plus a bunch of other things. And that's going to be equal to e to the theta x times x. Awesome. So now what are we going to do? Well, we have something that's now just in terms of, right, e to the theta x times x. We can actually find the Taylor expansion of this. If we treat theta x times x as one variable, which we totally can, we can Taylor expand that, and we'll get something that looks like the following. So I'm just going to write the same thing here down on the side. 1 is 1/2 x plus dot, dot, dot. That's going to be equal to, and then we get the same thing, right? That's going to be 1 plus, now what's going to come next? Theta x times x, right? Theta x times x plus theta x times x squared over 2, right? So over 2 theta x times x, the whole quantity squared over 2, right? And then we can get rid of a bunch of stuff, right? We can divide everything by x. We can also subtract those ones. So let me, in red, get rid of almost everything, right? One of those x's is going to go away. And essentially what this is going to leave us with is the following. Plus is equal to theta x. So this is what we get. We get that theta of x, the, Taylor series expansion of that, at least, is equal to 1/2 plus a bunch of higher order terms that involve x. And my claim is that we actually do not care much about those, because what are we doing? Well, we're taking the limit as x goes to 0, right? So let's take the limit of both sides. That will preserve our equality here. So the limit as x approaches 0 of 1/2 plus a bunch of things in terms of x is equal to the limit as x approaches 0 of theta of x, right? And basically what happens is all the stuff that's in terms of x is going to drop out, right? Because x is going to 0. This is our star player. This is what allows us to say, right, that the limit as x approaches 0 of theta x is just equal to 1/2. So this is what we really are concerned with. So I know that this is a rather complicated process, but basically whenever we see something and it's a relatively complicated equation where we're comparing similar but different things on both sides. So if we look at our original equation, right, we see that there's going to be an e to the x on this side. We see that there's going to be an e to the something on this side. We also see that the limit, right, is x approaching 0. These are two very big hints that we're going to use the Taylor series expansion and try to do some type of analysis with the terms of the Taylor series expansion, right? Because as x goes to 0, all of those higher order terms, other than that first initial one, is going to essentially become negligible. And that's why we can do that to look at the limit as x approaches 0. So I want to show you quickly what my original function looks like on Desmos and show you that, yes, the limit is indeed going to be 1/2. So bear with me for a second. All right, so I pulled up the graph, and I like to do this just because giving people a visual example is something that is sometimes really important. I know that it helps me a lot. We have this graph, right? And it's essentially equivalent to theta of x. And we see that as we drag our pen along the line, it gets closer and closer, right, to 0.5 as x approaches 0. But at 0, it's actually going to be undefined, even though that should be around 0.5.